Now let us have a look at some nonlinear differential equation. And one easy application is the following. Consider again a reservoir filled with water, but this time we make a little hole somewhere close to the bottom. Then the water flows out and the level decreases, it goes down. And we want to, we denote the height of the level h, and we want to find the function how h decreases with time t. We will need the conservation of mass and conservation of energy. So if we consider a small element of water, a small droplet of water flowing out, then the kinetic energy is 1/2 dm v squared. I write d because we consider just a very small amount of water, very small mass. And this must be equal to the potential energy or the potential energy difference between the height and the hole. So this must be equal to dm gh. G is the acceleration due to gravity, something like 9.81 meters per square second. And height is h is the height in meters. So we can divide by dm and multiply by 2, and we can express velocity v as 2gh. So that was the energy. And what about the conservation of mass? What flows out must be compensated by the decrease of volume when the surface goes down. If we denote this area as S1, and if we denote the area of this hole as S2, which will be typically much smaller than S1, then what flows out is velocity times time is this distance multiplied by the cross-section S2 is the volume of water that flows out in some small interval dt, and this must be compensated by the decrease of the height, which will be a S1, the area of the surface, times dh, the decrease of the height. But as h goes down, dh is negative, so we write minus. Well, and now when we substitute v from here to this, we get the differential equation for the unknown function h of time. So, well, and we can swap the left hand side and the right hand side, and we have dh is minus S2 divided by S1, v, which is square root of 2gh dt. And if we denote, say, h derivative, h prime the derivative of the height h with respect to time t, we have the differential equation h prime is minus S2 divided by S1, and we write it as square root of 2g, which is some constant, times square root of h. And this is our differential equation. It is a differential equation of the first order, because we have just the first derivative, and it is nonlinear, because we have a complicated function of h. We can solve this by separation. We see that h is equal to 0 is a solution What does it mean? Empty reservoir, no water at all, nothing changes, nothing flows out, nothing decreases, empty reservoir. Yes, this is a solution. And for h different from 0, we don't consider negative h. We assume that the water goes down and then stays at 0. It doesn't go to negative h. Well, we measure the height, not from the bottom, but from the position of the hole, if it is not at the bottom exactly. So if we divide by square root of h, and if we go back to dh dt and multiply by dt, we have h to minus 1/2 pH is, and this is some constant, minus s2 divided by s1 square root of 2g dt. And we can integrate, we can factor out the multiplicative constant in front of the integral. This is h to 1/2 divided by 1/2, that means multiplying by 2. Here we have this multiplicative constant, minus s2 s1 square root of 2h, t plus c. And we can give the integration constant c a physical meaning. Namely, at the starting point, at the initial situation, when t is 0, imagine that we have some initial height, let's call it h0. This is the initial value, the initial height of the water if we start observing the system. And if t is 0, then this is 0, and c has the meaning of 2h0 half. Then we can divide by 2, and we have square root of h is, let's start with this one, square root of h at 0 minus 1/2 s2 divided by s1 square root of 2g. Yeah, we can reduce this too, but this is not important. Well, and finally, h as a function of time is just square of that. Square root of h0 minus 1/2 s2 s1, t. So this is the solution to this differential equation that describes flowing out of the water out of the reservoir. It looks complicated, but this is a constant given by the initial situation. This is a constant describing the geometry and the gravitational field. So this is just constant minus constant times t, square of that. Quadratic function. So the graph is parabola. And as a function of t, the height h, then looks something like that. The parabola would continue this way, but this is not very physical. The level goes down, water flows out, and the level doesn't go up again. It doesn't go up, it stays at 0. Well, we can come to a conclusion. We can estimate the time it takes to empty the reservoir completely. This is the time, let's call it capital T, not period, it doesn't repeat, not period, but the time to empty the reservoir. And this is the time when h is 0. So if you write it as 0, then you can find the time t as square root of A0 divided by this constant. 1/2 S2 S1 square root of 2h. So you see the result of solving a differential equation may be either the complete function that describes the time evolution, or just some important parameter, some important property, the time needed to empty the reservoir.